This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question AB1 BC1, namely Riemann Sums. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here is an outline of the information presented in this video. I'll start by introducing some background information associated with Riemann sums and several assumptions that we make concerning the concept of area. I'll introduce summation notation and discuss some common summation formulas that can often be used to find a definite integral by definition. I'll talk about how we might estimate area graphically and using technology, and this will lead us to some formal definitions of Riemann sums. And finally, I'll present some examples and leave you with a few more exercises for class. First, a little bit of background information. One of the most important unifying problems in calculus is the area problem, and here's a statement of that problem. It says, suppose f is a continuous function and f of x is greater than or equal to 0. Find the area of the region S bounded by the graph of y equal f of x, the x-axis, and the lines x equal a and x equal b. And here's an illustration. The shaded area illustrates the region S, and we'd like to find the area of that region. Before we can begin to solve this problem, I think we need some assumptions about area, and we'll also need a review of summation notation. To start, here are some facts about area that we'll assume to be true. First, area is positive, and that means that the area of any plane region is a positive number. It doesn't really make sense to say that the area of a region is negative. Area is also additive, and that means that if we divide a region into non-overlapping pieces, then the area of the region is the sum of the areas of the individual pieces. If region 1 is contained in region 2, then the area of region 1 is less than or equal to the area of region 2. And finally, let's assume that we know the area of a rectangle, that is, that the area is equal to length times width. I think these assumptions suggest that we'll need to add the areas of lots of rectangles, and therefore we need a compact way to write long sums. Here's a brief review of sigma notation. The sum of n terms, a sub 1, a sub 2, all the way down to a sub n, can be written in the following manner, and this is read as a sum from I equal 1 to n of a sub I. This is called sigma notation because the symbol here is the Greek capital letter sigma, or S, and S stands for sum. The letter I in this notation is called the index of summation, or the summation variable. It's really an arbitrary variable or a dummy variable. The number 1 is the initial value or the lower bound, and the number n is the final value or the upper bound of the summation. Remember that the notation a sub I is shorthand, really, for a of I, indicating that a is a function of I. There are also some important properties of summations that we'll need to use in order to estimate areas. In the first one, let's assume that k is any constant. This says that the sum of k a sub I is k times the sum of the a sub i's. And in words, this says that constants pass freely through summation symbols. The second property seems pretty reasonable, and it simply says that we can split a sum or a difference into two separate summations. Here are some common summation formulas. In each case, let's let c be a constant and n a positive integer. These formulas will allow us to simplify lengthy summations. Do you remember how to prove some of these? In this example, I'd like to use the area assumptions and the properties of summations to estimate the area of a plane region. Let's see if we can estimate the area of the region S, bounded by the graph of y equal x squared, the x-axis, and the lines x equals 0 and x equal 1. And here's an illustration showing the region S. Just quickly looking at the area of the region S, I know that the area must be between 0 and 1 because the region S is contained in a square with side of length 1. But I feel like we can certainly find a better estimate than this. Let's start by dividing the region S into 4 pieces or subregions, S1 through S4. And we'll do this by drawing vertical lines at x equal 1/4, 1/2, and 3/4, as shown in this figure. We can approximate the area of each piece by using a rectangle. And each rectangle will have the same base as each subregion, and the height will be the same as the right edge of the subregion. So the height of each rectangle is the value of the function f of x equal x squared at the right endpoint of the corresponding subinterval. So each rectangle has width 1/4, and the heights are 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared. Let's let R sub 4 be the sum of the areas of these approximating rectangles. And here is that sum. And that's equal to 0.46875. Now I think we can tell by looking at this figure and the way that we constructed these rectangles that the area A of the region S has got to be less than that sum, 0.46875. Now we can also use rectangles constructed in a different way in order to obtain another approximation for the area of the region S. For example, suppose we use rectangles with heights equal to the values of the function f at the left endpoint of each subinterval. And here's an illustration. The sum of the areas of these approximating rectangles will be denoted L sub 4, and here's the calculation. L sub 4 is equal to 0.21875. Now, by looking at the figure, I think we agree that the area of the region S is certainly larger than L sub 4. And so now we have a lower and an upper bound for the area of the region S. It seems pretty reasonable that in order to obtain a better estimate of the area of the region S, we can divide the region into smaller pieces, and then we can use even smaller and thinner rectangles. So these two figures show better approximations for the area of S using 8 rectangles of equal width. The sum of the areas of the smaller rectangles, L sub 8, and the sum of the areas of the larger rectangles, R sub 8, provide better lower and upper estimates for the area of the region S. We can obtain even better estimates for the area of the region S by increasing the number of subregions, or equivalently by increasing the number of rectangles. I used the TI-Nspire to create a table of estimates. If you stare at that table long enough, it seems to suggest that both R sub n and L sub n are approaching 1/3. There are certainly lots of other methods that we could use to approximate the area of each of these subregions, and then we could add those areas to approximate the area of S. However, let's consider some generalizations of the 2 models that I used in the previous example, and 2 additional approximating sums. In general, let's consider a plane region S bounded above by the graph of a non-negative continuous function y equal f of x, below by the x-axis, and on the left by x equal a and on the right by x equal b. Here's an illustration. Divide the interval a to b into n non-overlapping subintervals as defined by these values. This is called a partition of the interval a to b, and here's how it's denoted. This is a visualization of the partition P. Again, we've divided the interval a to b into n subintervals. To continue with this generalization, let's let delta x sub I be the length of the ith subinterval. Remember that the subintervals do not all have to be the same length. Let x sub I star be an arbitrary point in the ith subinterval. Then a Riemann sum of the function f over the interval ab with partition P is given by this expression. For any given partition, different Riemann sums are obtained depending upon how we select these values x sub I star. If x sub I star is the left endpoint of each subinterval, then the sum is a left Riemann sum, usually denoted L sub n. If x sub I star is the right endpoint of each subinterval, then the sum is a right Riemann sum, R sub n. And if x sub I star is the midpoint of each subinterval, often denoted x sub I bar, then the sum is called a midpoint Riemann sum. Now, instead of using rectangles to estimate the area of each subregion, we can also use trapezoids. It's kind of hard to see in this figure, but I am approximating each one of these subregions with a trapezoid. And for a given partition, the sum of the areas of these trapezoids is called, well, a trapezoidal sum, denoted T sub n. And it turns out that a trapezoidal sum is the arithmetic mean of the corresponding left and right Riemann sum. If we divide the interval a to b into equal subintervals, then the partition is called regular. In this case, the length of each subinterval is the same. So delta x sub I is constant, and it can be written as just, well, delta x. And this length is equal to b minus a divided by n. And the points in the partition are a plus delta x, a plus 2 delta x, and so forth. So if we have a regular partition, the left Riemann sum is written in this way, and here's the right Riemann sum. If we have a regular partition, the midpoint sum is written this way. And here's the formula for a trapezoidal sum if the partition is regular. Be careful. Some students memorize and use the last line here for any trapezoidal sum, but this is only valid if the partition is regular. In example 1, the region S is bounded above by the graph of y equal x squared, below by the x-axis, and the lines x equals 0 and x equal 1. Let's use a regular partition and extend the table to include midpoint and trapezoidal sums. Well, I use technology to produce this table, and here are some observations. It certainly appears that each sum is zeroing in on or approaching the exact same value, 1/3. And it looks like the midpoint sum and the trapezoidal sum approach this limiting value faster. All of these sums in the previous slide are just approximations. It certainly looks like the limiting value is 1/3, but it would be really nice if we could confirm this is true analytically. So let's try to show that the limit, as n goes to infinity, of r sub n, the right Riemann sum, is 1/3. We'll use a regular partition. So we'll divide the interval 0 to 1 into n equal subintervals. So each of them will have width delta x, which is 1 minus 0 b minus a divided by n, or just 1 divided by n. So the partition is made up of these values, 0, 1 over n, 2 over n, all the way up to the right-hand endpoint of the interval, 1. Let's start by writing out r sub n and trying to simplify. Here's the expression for r sub n if the partition is regular. In this step, I wrote out the summation and evaluated the function f at the right endpoint of each subinterval. Next, I factored out a 1 divided by n cubed from each term. And then I used one of the common summation formulas and simplified to get this closed form expression. Remember, this is the value of the right Riemann sum for any regular partition, that is, for any value of n. Now let's try to evaluate the limit as n goes to infinity of r sub n. First, I'll rewrite the expression for r sub n as a product. And then I'll rewrite each fraction really as two separate fractions, so that each term is expressed as a sum. Now, as n goes to infinity, we know that 1 divided by n goes to 0. Therefore, the overall limit here is 1/3. That says that the exact area of that region S is 1/3, and that's a pretty amazing result. I think these examples suggest that we can define the area of the region S to be the limit of the areas of the approximating rectangles. And it can be shown that we get the exact same limit if we use a left Riemann sum instead. And in fact, we could take the height of the ith rectangle to be the value of f at any number x sub I star in the ith subinterval, and the limit as n goes to infinity of this Riemann sum would be the same. Here's another way to think about this limiting value a. We could, if we wanted to, approximate the area of the region S by forming lower and upper sums. So, for example, we could select x sub I star so that f of x sub I star is the minimum, or the maximum, value of f in the ith subinterval. And then a would be the unique number that is smaller than all of the upper sums, but bigger than all of the lower sums, so that the upper and the lower sums sandwich or squeeze the area of that region S. So let me leave you with this example. Let's let A be the area of a region bounded by the graph of f of x equal to 1 divided by 1 plus x squared, below by the x-axis, and between the lines x equals 0 and x equals 3. Using right endpoints and n equal subintervals, therefore a right Riemann sum and a regular partition, find an expression for A as a limit. That means find the limit expression. Don't evaluate the limit, but find an expression for the area expressed as a limit. Estimate the area using a midpoint sum and a trapezoidal sum with n equal 4 and n equal 10. And carefully sketch a graph using technology to illustrate each sum for n equal 4. Use technology to construct a table of values for a left Riemann sum, right Riemann sum, midpoint sum, and trapezoidal sum for various values of n, and use this table to estimate the exact value of A. I hope this video provides insight into Riemann sums, a few AP Calculus type problems, and the use of technology to explore Riemann sums. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.